Okay, so let's go to start. Hello everyone and good morning from Seville, Spain. Welcome to the webinar from European project Grasshopper. I'm delighted to see many of you here following us in this online event. I'm Maria Tejada. I'm chemical engineer and the project manager of Grasshopper from Abengoa site, and I have the pleasure to introduce this session today. This meeting will last for about 1 hour, and it will be a beginning presentation and a final section of question and answer. The purpose of this webinar is that all of you know a little more about Grasshopper project and how the partner has worked to achieve the objective of the project. I will go quickly through the agenda, which is really simple. After my short introduction, we will explain you why Grasshopper is, and we will go through the main work packages. For this section, we have the pleasure to have with us some representation from each partner who form the European consortium. They will be also available for the question section at the end of the event. We will show you also a brief sample of the testing result from the operating the pilot plant and a virtual visit to it. And at the end of the presentation, we could answer your question. You should ask any question that you have via the chat, which is available in this application anytime during this session. And if it's possible, we will appreciate it if you could indicate it which partner is for. So with further delay, go ahead. So why Grasshopper? Well, Grasshopper is an European project. We have received funding from the Fuel Cell and Hydrogen, now Clean Hydrogen Partnership, and then the European Union Horizon 2020 Research and Innovation Program. It integrates several partners, and each of one lists 1 or 2 work packages, which we will explain next. The Grasshopper project aims to realize a next-generation fuel cell power plant targeting stationary application at the megawatt scale for grid stabilization. The plant also has to have a flexible power output, an important reduction of capital expenditure. We are 6 partners in the consortium, and we have to thank you, the European Commission, which has provided us the opportunity to work with an international group of people using the European funding. So let me introduce you all of us. CBT, located in Duisburg, Germany, which is one of the leading research institutes in Europe for fuel cell and hydrogen technologies. Johnson Matthey, from Sweden, United Kingdom, is a company leading catalyst and membrane electrode assemblies, supplier for fuel cells. Nestag, from Arnhem, Netherlands, is a company that manufactures and commercializes PEM fuel cell stacks with more than 20 years of experience. They have also vast experience developing PEM power plant. Politecnico di Milano, Italy, specifically the group of energy conversion system, which has a wide and recognized background on power plant and energy system simulation and optimization, focusing on advanced energy conversion system. INEA is a leading company in Ljubljana, Slovenia, in the field of energy management solution, industrial automation, process computer control, and manufacturing informatics. And Abengoa, from Seville, Spain, a technology company that applies innovative solutions for sustainable development, infrastructure, environment, and energy sector. Well, so now that you know more about the Grasshopper team, let's talk about the characteristics which make this project different. And as I mentioned before, the project aims to develop a next generation of fuel cell power plant targeting stationary application in the megawatt scale, and looks for a cost reduction and a flexible operation. Although the technical feasibility of hydrogen fuel cell power plant has well demonstrated, a significant step in cost reduction is still needed. So one of the project aim is to reduce this cost. And when we say cost reduction, we are talking about a capital expenditure of less than 1,500 € per kilowatt, halving the cost of previous projects. The megawatt site unit design is based on the learning from a 100 kilowatt pilot plant, which we are now testing in Seville. Right now, we are almost finishing the FET period, and after that, the plant will be shipped to the Netherlands, where it will be connected to a residual hydrogen flow produced by a chloralkali industry. Also, the plant has the novelty compared to the conventional fuel cell power plant, which allows a dynamic and flexible operation that could run from 20 to 100% load for a demand-driven operation. And to achieve a competitive product, the plant is autonomous, which means that the plant can operate without the need of an operator, allowing the plant to be run in a remote location. So the plant could be running in a remote location, and we can supervise it here from Seville, for example. And looking the same objective, the plant is designed in a containerized solution for an easy plug and play installation. The major costs have been achieved by development new stack of larger size and higher power density, and and membrane electrode assemblies with long lifetime and lower cost. Also, from the part of the balance of plant, we have looked for commercial equipment, optimization in material selection, and trying to reduce as much as possible the number of connections and elements. Although the pilot plant is intended for grid balancing, its versatile design allows it to be adapted to other applications, such as power-to-power, off-grid, or energy generator. I guess now you have a general vision of the project, so let's go into details. Our partner, CTBT, has worked in the model development and validation of a large area flow field, and our colleague, Sanke Guslin, Director of Simulation and Control Group at CTBT, will show us this flow field development. So, Sanke, please.
Yes, can you hear me?
Yes.
Thank you for the introduction, Maria. So, ZPT was responsible for some key topics regarding the new Grasshopper stack. Therefore, we have analyzed the existing stack technology from NetStack and the existing MEA technology from JM. And we have identified the technical limitations of the designs, and especially from the combination of these designs. And then we have made a simulation and development of a new flow field. And then we have tested this new flow field for the operating point that we have developed with all the relevant partners. We have validated this new design on a 25 square centimeter test cell base. And the result of these tests was that we have even exceeded the performance target. And under certain operating conditions, we were even able to further exceed this target performance. This is very important if you have to address some end-of-life topics where there has been taken some degradation place within the fuel cell stack. All these developments have been made on the 25 square centimeter test cell design. And then, Maria, please go ahead. And then we have translated, thank you. Then we have translated this new flow field that we have tested within the test cell to the 300 square centimeter active area from the new Grasshopper stack. And this design has been finally validated within measurements. But what ZPT has done was a simulation-based validation of the new design. So we have checked within CFD, multi-physical CFD simulations, that we have a very good homogeneous humidity and current density distribution for the full stack, so that on the whole surface area we have very good operating conditions. And very new in our technology at ZPT, we have made some simulation-based degradation analysis to prevent that we have some local hotspots causing degradation and reducing the lifetime of the fuel cell stack. And the good thing is that we do not see any local hotspots for the degradation. Of course, there are differences at the cathode inlet or the cathode outlet regarding the degradation, but this is related to the technical operating conditions with low stoichiometries. And we thus have a good validation of the new Grasshopper stack design.
Thank you, Sonke, for your great explanation.
You're welcome.
Let's go next with Paddy Hayes, lead scientific at Johnson Matthey Fuel Cell. They have been working on the improvement of the MEAs with long time and lower cost. And Paddy is going to explain us the excellent result from his side. So please, Paddy.
Thank you, Maria. Thank you. And thank you everyone for coming to listen to us talk today. The heart of any fuel cell is the membrane electrode assembly, MEA. Johnson Matthey Fuel Cells have been making membrane electrode assemblies, MEAs, on a commercial basis for around 20 years now. And in that time, Johnson Matthey have in the past sold MEAs to customers for stationary power plants of the type that Grasshopper was built on, and we're also increasingly developing high volume, high performance catalyst coated membrane (CCM) methods for the automotive range extender market. Previous stationary power MEAs, they were very robust, very durable. They were hand built, so they were built by technicians working on the line, and they tended to have very high costs, including a high platinum loading to ensure that long life. By contrast, the emerging catalyst-coated membrane technologies is made in much higher volume, an automated roll-to-roll method, which allows for reduced costs. But that type of CCM, that type of catalyst-coated membrane, is very optimized for the demands of the automotive, the vehicle fuel cell market. So our challenge in the Grasshopper program and the GRASS at the start of Grasshopper stands for grid assisting, was to come up with an MEA that could realize the benefits of this lower cost whilst providing good performance and good lifetime for a grid assisting, so in other words, a flexible stationary power plant application such as this. We did this by taking the catalyst coated membrane technology, adding some additional thickness to the membrane, so taking the membrane electrolyte from 15 microns up to about 20 microns, adding additional reinforcement, additional chemical stabilization to prevent the degradation methods that are common, increasing the loading, but not increasing the platinum loading by very much. And the important thing to note here is that compared to the previous stationary power applications, the platinum loading was reduced by around about 80%. So all these methods, all this ability to realize the benefits of the automotive type CCM technology allowed us to reduce the platinum loading by around 80%, but we had to take some steps to prolong the lifetime, the likely lifetime, the durability of the resulting CCM. And after our initial testing and approval by NEDSTAC FCT, JM settled on this Grasshopper 3 GH3 CCM, optimized for stationary grid support, but with those additional stabilizations. So JM, because this MEA had been designed with volume manufacture in mind, we were then able to take that MEA design to our high volume manufacturing equipment, much fewer manual processes, much more automated roll-to-roll type processes. And after some prototype scale runs, we made around 2,000 MEAs on that high volume manufacturing equipment. That's been built into stacks for the 100 kilowatt pilot plant by our partners NEDSTAC. Those stacks in turn have been shipped to the pilot scale plant at Abengoa in Sevilla, and they're being tested in that plant at the moment. But more importantly than that, Johnson Matthey Fuel Cells tested those MEAs pretty extensively to understand how they'll perform and how durable they're likely to be. Maria, could we have the next slide, please? Thank you. We put the Grasshopper MEA up against the existing catalyst coated membrane. So a catalyst coated membrane that was designed more for the demands of the automotive market. And it's a pretty durable MEA. It's done well in the automotive market, but the important point to note is that for the stationary power, we're looking for longer life and a higher proportion of time operating and a flexible operating regime that would allow it to work well in a grid assisting power plant. And you can see from this that the red, blue, and green traces, which is the performance of the Grasshopper CCM against time, thank you, far outperform the durability and the likely lifetime of the gold, light blue, and purple traces for the automotive type CCM that was in existence in around about 2018 when we started this project. And in fact, given that there's a small amount of performance gain at the start of the project, the start of the 10,000 hours or so of testing, followed by a very, very flat current density, sorry, voltage versus time trace for the low, high, and intermediate current density points. The Grasshopper MEA essentially showed minimal decay, very little decay at all, over 10,000 hours testing in this drive cycle. There are more details of the drive cycle and the measures we used to test it in the publicly available reports at the end of the program. So you'll be able to read in a bit of detail about how we chose the drive cycle and why we chose this particular way of testing it. But the conclusion that from Johnson Matthey's work at the end of this program is that we've delivered an MEA with significant durability improvements, ease of manufacture, far lower platinum loading, about 80% less platinum than the stationary power MEA, but much greater durability and performance stability than the automotive type CCM that was in existence 3 to 4 years ago when we started this project. Thank you.
Thank you, Paddy, for your great contribution. So we have the flow field, we have the membrane, just we need the fuel cell stack. So it's turned to NESTAC. NESTAC has improved the stack design and had led its pilot construction. Your Colehan, managed customer development and project at NESTAC, we will be giving us a short presentation of the new stack development. So please, George.
Okay, so I will continue. So as Maria has explained, we have done some work on the flow field by ZBT. We have developed an MEA, and obviously we need to integrate this to a stack, which now needs to be of quite a different type as that NetStack had available pre-project. So in order to get the cost targets down, the power density needs to be increased, and we need the stack needs to be capable of having a fast load responses. So a completely new stack platform has been developed, going to a 50% larger active area, allowing the stack to operate with overpressure and in close cooperation with ZBT, as Sunken has already mentioned, a completely new flow field has been developed. In the next step, we have actually built those stacks. So to the 300 square centimeter active area platform, and we have tested them and demonstrated the original target power density could be achieved. We have unfortunately faced some delays in the actual manufacturing of the large stacks, which has resulted that an intermediate stack platform has been supplied to Abengoa and has incorporated the Johnson Matthey GH3 MEAs to demonstrate the power plant technology in the pilot plant. So in the next sheet, you can see some examples. On the right side, you see that the optimized flow field for the fast dynamic responses is shown there. At the left middle side, you see that in order to get to lower cost targets, we have changed the seal design. Also, this has been done together with ZBT to apply dispense seal technology. And then finally, on the right bottom side, you see the actual stack. Several stacks have been built and have been tested, incorporating Johnson Matthey's GH3 MEAs, and the results can be shown in the next slide. So here you see first on the right-hand side, you see the large stack as it is, and on the left side you see that the performance at the slightly elevated pressure of 0.6 bar G back pressure, as it was originally intended, is actually exceeding the project target of 0.68 volts at 1 amp per square centimeter. And it has been tested at various conditions, but the originally targeted one is above the project target, and this will result in the actual stack power of 25 kilowatts, which was the original project target.
Okay, thank you, George, for your interesting presentation and for your great work. And it's time to Politecnico di Milano, and all of you should know that all the work for the power plant needs a previous system modeling, and Elena Crespi, a PhD student from Politecnico di Milano, is going to explain us a little about the helpful system modeling. So please, Elena.
Yes, good morning, everybody, and thank you, Maria, for the introduction. So as Maria said, in Politecnico di Milano, we had the task to develop a simulation model of the fuel cell power plant, models that are useful to optimize the fuel cell system design and operation strategy. So I'm going to tell you something about the dynamic simulation model of the Grasshopper plant that we have developed. The model includes all the pilot plant components, and for each of them we have realized a model that shows mass and energy balances during dynamic operation of the system. As regards the fuel cell stack, the electrochemical performance were modeled through semi-empirical polarization curves, and then we have combined the components model together to reproduce the layout of the 100 kilowatt pilot plant. That is the layout you can see simplified in the picture in this slide. And finally, we have modeled also the control system, including PI type and on-off controller inside the model. The next step was the calibration. Previous slide. Okay, the calibration and validation of the model with so that was performed comparing the results of simulation to experimental data collected during the preliminary test of the pilot plant. And for example, in the picture you can see an example of this type of comparison. And overall, the procedure showed that the model is able to reproduce with a good accuracy the stationary and the dynamic behavior of the system component. So, for example, the model was used to help setting up the control system of the pilot plant. And in the next slide, you can see another application of the model. That is the optimization of the design and operation strategy of a 1 megawatt system. So in the perspective of scaling up the system for commercialization. So the model was used to simulate the plant warm-up and load following operation. And the simulation have compared the system behavior for a 100 kilowatt unit to the behavior of a 1 megawatt unit. In this way, we pointed out the main criticalities of the scale-up And we also propose some solution to optimize the design and the operation strategy of the 1 megawatt system. For example, the simulation has shown the importance of the choice of the warm-up strategy because the current set point of the stack affect the warm-up time. For example, in the figure that you see in this slide, you can see that with higher current density, that is the plot on the right, the current temperature reaches the set point much faster. As regards the load following operation, you can see in the figure on the right that the system is able to follow stepwise changes of the current set point with no negative impact on the system efficiency. And in this way, we proved the flexibility of this plant. So overall, we can say that the model is a tool that can be useful for the optimization of the commercial systems. That is the final goal of the project.
Thank you, Elena, for your helpful work for this project. And finally, Marie-Jeanne Widmar from INEA, which apart from being the project coordinator, provide advanced solution for flexible fuel cell power plant operation and grid support services. And Marie-Jeanne is going to explain us about the plan for to grid integration. So please, Marie-Jeanne. You are mute.
Yeah, okay. Good morning, everybody. Thank you very much for the introduction. And well, I will shortly explain what was the aim of INEA to integrate the fuel cell system into the grid. So nowadays, the grid is more and more translated into the smart grid, so-called smart grid system. The demand is a very important factor. So INEA has provided an interface. We call that smart grid interface that is able to connect the control system, which is, let's say, wider, more services together to the fuel cell system that is basically providing the electricity to the grid. There are a few different things inside this integration module. So one thing is that it could cooperate in the selling process inside the smart grids, could provide the system services that are important for keeping grid stable, and could do that without manual operation. So everything could go automatically. Besides that, of course, there is a need for the real-time exchange of data with the service provider. Next slide, please. Besides that, the system is able to do that. It's also very important that could be scalable. So the interface could connect several fuel cell systems together to cooperate with the demands, responses that are needed for the let's say optimized operation of the system inside the smart grid. Yeah, maybe one thing is important that these demand requests are still, let's say, in the early phase on the market. So it's still inside development in different countries, different providers, and we at INEA try to do that as much standardized as possible at the moment. That will be in short.
So thank you, Mary-Jan, for your presentation. And now we are going to explain all of you the pilot plan from Abengoa side. Abengoa has developed the 100 kilowatt prototype, the design, the construction, and the testing. And we have also designed the megawatt site. Additionally, we have done all the work related to the project diffusion, as you can see with this webinar. In this turntable of the plan, you can see as the pilot plan is a continuous size solution, and it's physically divided in two areas. One is for the process, and another is for the electrical compartment. The process compartment is physically separated from the electrical area because of safety reasons, such we are working with hydrogen. As a fuel cell power plant, the heart of the plant is the fuel cell, which generates electricity, heat, and water through a combination of hydrogen and oxygen. So we can distinguish as main functional units inside the container the fuel cell, the air, and the hydrogen, without forgetting, and non less important, the power conditioning system. In the process area, both the air and the hydrogen inlets are conditioned before going to the fuel cell, and it controls their flow and pressure, and they increase the relative humidity while pollutant are removed. In addition, they increase their temperature thanks to the heat generated by the electrochemical reaction inside the fuel cell. The fuel cell module, as we told before, can operate from 20 to 100 load, and a continuous cell voltage monitoring allows the control of the balance of plant component to effectively respond to the dynamic load condition while increasing the fuel cell lifetime. The power conditioning system transforms the DC produced by the fuel cell into an adequate AC power that can be injected into the grid. In addition, the plant is a self-sustainable system, providing its own power consumption, capable of operating in a warm standby mode with zero net power value. Additionally, the plant has auxiliary circuits such as nitrogen for inertization or cooling circuits for a temperature control. In this slide, you can see the process with more detail. And as I mentioned before, the air and the hydrogen must enter to the stack with a controlled relative humidity, because the membrane has to be humidified to operate in a good condition. This humidification is done with the water that is generated in the fuel cell. So the plant has not water consumption, just only in the first startup. The fuel cell has to operate in a constant temperature, and as the electrochemical reaction is exothermic, a constant temperature is necessary to avoid the thermal degradation. So an internal cooling circuit is needed to remove the excess of this heating, and it's used in this cooling circuit for preheating the reactant, as you can see here in this heat exchanger. In the case of the pilot plant, there is a need for an extra cooling to remove the excess heat, but this could not be necessary if you are in an industry and it needs warm water, so we could take advantage of it. I don't want to be very repetitive, but a precise control of flow, pressure, temperature, and humidity is done to achieve the dynamic operation, because each point needs a specific parameter depend on the load. We have also worked in the system rapid response to load change demand, and we have defined control strategies for maximizing the fuel cell and the plant lifetime, as improved shutdown or the control inertization. Behind all the engineering work of the balance plant, there is an extensive joint effort in all disciplines, where safety all comes first. The engineering design of the plant has been carried out without ever forgetting that we are working with hydrogen, and all the appropriate measures have been taken to work without risk. So we have done hazard reclassification studies, automatic safety strategies, hydrogen leak detector, and along etc. And as you can imagine, in such crane space, in a container, it is important to not forget the maintainability of the plant. So the plant has a well-defined maintenance plan, and the PLC is able to alert the operator when a maintenance is required. So that is really important if the plant is in a remote location. And all the equipment can be extracted for a major overhaul. So this is mainly the description of the process area, and to explain the area more related to the electrical marker and the results, my colleague Germán Nieto will continue with the explanation. So Germán, please, could you introduce yourself and go on?
Thank you, Maria. I'm a process engineer, also from process and testing engineer, also from Abengoa side. One of the key aspects of the project is to participate in the electrical reserve market. The main reason is that usually this service is paid at a higher price than baseload generators. This would allow hydrogen fuel cell power plants to penetrate sooner as a commercially established product, as Ainea has said before. We have selected the European Manual Frequency Restoration Reserve. Probably you all know that each country has its own shape of the reserve market, but they are unifying into automatic frequency restoration reserve and manual frequency restoration reserve. You can see in the graph, the bottom right, what are the requirements to participate in this market. As a result, the system must be flexible, fast-acting, and autonomous. And it was our intention with the pilot plant to address all of this above. A single bidirectional power connection for the grid allows for very precise control of the net power that is being injected, integrated communications interface that Ainea has explained before, allows the plant to participate in smart grids, integration into virtual power plants. Everything is, and the platform is cloud-based, so everything is very easy to join efforts with other prosumers. And the goal is basically to participate autonomously in the bidding and the electrical market in the operation. So now let's go through some of the results that we have get with the pilot plan. The testing phase of the pilot plan has several stages. During the first stage, we focused on the plant itself, adjusting control loops, making sure that everything was working before we installed the stacks. So no power was being produced during the first steps. And then during the second stage, with these intermediate stacks that Nestak George has mentioned before, already including many improvements that the previous stack had. So we installed these stacks and we started the power production testing. In this critical step, all previously tested strategies were validated, many tests were carried out, warm-up sequences, shutdowns, dynamic load changes, etc. Of course, during this period of time, only synthetic hydrogen was used to ensure that no damage was done to the stacks. Finally, the last stage of the testing period here in Abengoa's facilities in Seville is the factory acceptance test, or FAT. Although all those covered before, all those tests done before cover all the performance and the rapid responses. Once this FAT is completed, the plant will be shipped to the Netherlands, where it will be connected, and we will talk a little bit more about that later on. But you can see, for example, in this summary in this slide, that the results obtained from the testing are very promising, and the plant has a great potential to participate in the electrical market and grid balancing services. You can, for example, see that the maximum net power of 80 kilowatt. We have to talk about a pilot plant of 100 kilowatt. That is gross power, so it's DC power produced by the fuel cell itself. 80 kilowatt of net power. And you can see, for example, here, starting from cold standby, around 15 degrees, we reach maximum power in 15 minutes. This type of let's say startup strategy has been decided with all the consortium to ensure that we can compare the degradation of the stacks from the beginning of life to the end of life. So in some specific application, this could be different. We can define a different starting strategies, but the starting strategies for this plant always go from 0 to 100%. Then you will see here load change steps. Going down is actually instantaneous, less than a second to change that. And then you see here, for example, steps from 50% power to 100% power in less than 20 seconds, and from 0% to 100% in less than 1 minute. This will allow the plant to participate in the manual frequency restoration reserve that we have been talking about before. So it shows great potential for it, and we cannot wait to put the plant in the Netherlands to actually have it running. Yeah, and this section that you see here in the warm standby is actually the plant being running. It has a minimal consumption of hydrogen, of course, but because we only have one grid, only one electrical interface with the grid, the net power is absolute zero, which is great if, for example, in some congested some areas with electrical congestion, we have DCOs tell us that they need to shut down specific some power generations immediately. So we also show this capability here. If we go a little bit more in detail in what we saw in the graph before, you can see, for example, here the 100 gross kilowatt power. You can see some of it is lost, of course, in the conversion from the DC to the AC, and then the other half is lost in the powering of the pumps, the compressor, and all the auxiliaries. The loss of the power conditioning system, though, this will be greatly reduced in a megawatt scale system, because this is a small system, there's a small plant. The losses are bigger than we should expect in a commercial plant in the power conditioning system. And we have been talking a lot about, in all partners, we have talked about life expectancy of the stacks, and we have put a lot of effort as well in expanding the lifetime of the hydrogen fuel cell. In this slide, you can see, for example, one of the strategies implemented known as oxygen depletion. And the graph shows a very homogeneous reduction in the fuel cell. So each data point in this axis represents one of the individual cells. You can see how very homogeneously the cell voltage is being reduced across the whole stack, which is a very good result that makes us to believe that we are in the right direction to expand the lifetime of the stacks. Especially critical for generators that are continuously shutting off, starting up, like in this case, providing grid services, microgrids, portable or emergency generators. as you can imagine, there are a lot more interesting results to talk about, not only from Abengoa, from all the partners, but we don't have much time. So let's continue forward. Don't forget to put your questions in the chat. We will ask them if we have time at the end of the presentation. So what is the next step of the project? Are to transport the pilot plant to the Netherlands, where we will be using a residual hydrogen stream from chloralkali industry. There, the plant will remain there for 5 years, where we will be collecting degradation data, operation cost data, or everything that will improve the design of the megawatt design that we already have developed in the consortium. And of course, like we have seen before, the goal is the project is not to end in the pilot plant, is to have a megawatt scale plant that can be commercially used as soon as possible. And for that, we have been implemented all the lessons learned in the pilot plant, including, and this is where we want to reach the reduction of the costs, etc. Very briefly, going through the applications, because we don't have much time. Although the goal of the project is to provide grid stabilization services using a residual hydrogen stream from a chemical plant, this is not the only application that we have explored, and this is the uses. So it can be directly used in a chemical, like we see, use it here in a chemical compound to use the residual hydrogen. It can be used for low temperature cogeneration, but also it can be used as a mobile and temporal generator, much like conventional diesel gensets, as an emergency generator for critical loads like hospital, data centers, air traffic controls, base load generator for microgrids, and of course integrated into a power-to-power system combined with renewable energy sources to reduce energy imports from other countries or parties. We are all seeing in these turbulent times how important it is to be energy independent. And now, thank
you, Germán, for your understanding and an exciting presentation. This gives all of you a much clearer idea of what Grasshopper is all about and how the fuel cell power plant can be a great alternative to the much needed decarbonization. And to finalize, we will show you a virtual visit to the pilot plant, and after that, we will pass to the question time. So let's go to the visit.
Hello, my name is Maria Tejada, the technical manager of Grasshopper project from Abengoa side, and I'm here with my colleagues in the test facilities. I guess most of you know already a bit about our plan, so now it's time for a virtual visit for your enjoyment.
Hi, I'm Lucia Martinez, the mechanical engineer. We are located in Seville, from where we are operating the pilot plant.
And I'm Germán Nieto, process and testing engineer, also from Abengoa side, and we're going to show you the pilot plant. Let's go.
From this side, we can see the process area, physically separated from the electrical compartment for safety reasons. The equipment is grouped into two separate skids. On the left, the air is compressed, filtered, and humidified. On the right, the hydrogen feed goes through the same steps. For charge purpose, water is recovered at the condenser from the outlet streams, and heat is distributed and removed using a coolant subsystem. Although it is hard to believe by what you can see in this image, almost all equipment that needs a periodic maintenance task is accessible, and if a major maintenance is required, the mentioned skids and mounting on rails for easy extraction.
When working with hydrogen, safety is always a priority. There are many layers of protection in place. To name a few: forced ventilation that ensures no accumulation of hydrogen inside the plant, emergency buffers of nitrogen for circuit inertization, hydrogen detectors to identify leakages, and ATEX instrumentation and cabling for hazardous areas. Another step forward to reduce cost was made in the gases distribution manifold for the fuel cells, quite impactful in the stable operation of the system, but also in the cost of a large megawatt-scale power plant.
Here you can see the heart of the power plant, several stacks of PEM hydrogen fuel cell with a total gross power of 100 kilowatts and an efficiency over 55%. It has the added value that it is also able to operate from 20 to 100 watts without sacrificing its lifetime. Fuel cells are very great power generators. They are silent, they only produce water as emissions, and they are very stylish. But they are a passive device, which means a robust and reliable balance of plant is mandatory for an optimal operation at any load point.
PEM fuel cells produce DC power, therefore it needs to be transformed into AC power. This is the role of the power conditioning system, a critical part of the balance of plant. Along with it, you can also find the auxiliaries power cabinet and the control cabinet in this compartment. If the stacks are the heart of the system, this is the brain. Using a cloud-based interface, the plant operates remotely and without supervision. In the final destination, it will participate in the electrical market autonomously, joining other prosumers in a virtual power plant.
Okay, then let's
So I hope that you have enjoyed the visit. It's a pity that due to the COVID situation, this webinar have changed to the virtual mode. It will be better if you can join us here physically, but it's better than nothing. So now we would love to hear from you. It's just the time to finish it, but we can longer 5 or 10 minutes. And so let's go to the first question, Germán.
Yeah, so by order. So it says, I'm Joseph from Spain. First of all, thank you for the webinar. You have mentioned that the plant is destined for grid balances as well as lithium batteries. So what is the main difference between this kind of power plant and batteries? So that's a very interesting question because we get that often quite a lot. Lithium batteries have great response time, but their energy capacity is limited to the reactants inside inside the battery. So the main advantage is that you can decouple power capacity and energy capacity, especially if you are talking about storage. If you want to storage more energy, you have to install more batteries, which means more lithium, and the cost will increase, not exponential, but will increase as we go to higher energy capacity for storage. This do not happen with the hydrogen. Of course, you still need a bigger hydrogen tank, but it is as we go to higher capacities, it is cheaper because using hydrogen, because you don't have to increase the number of stacks to have more energy. You just need a bigger tank of hydrogen. So that is the main advantage. Yeah, that's it.
So Elizabeth asked us which is the software used for the system modeling and for the grid balancing interface. We use the Siemens.
Well, I think they're referring to modeling, so Pauline, maybe
Oh,
Elena.
okay, Pauline
Yeah.
should ask
Yes.
the question better.
Okay, so I can answer to this question. For the modeling of the system, we use the software Simulink from MATLAB. And if you want to know something more about the model, we are going to publish soon a paper on the model itself. So in a few months, I think, or week, you will be able to know something more.
Thank you, Lena. And the other one is, and the grid in balancing interface, maybe Marijan will ask better than us this question.
Yeah, okay. Inside the interface itself, it's the communication with the standard control system of the fuel cells. That's done via standard Modbus connection. To the outside, to the grid services, we are working with the JSON messages that are traveling over the internet.
Okay, so go on the next one. Say, Angel Guerra from Spain asks, what is the quality of the water produced by fuel cells? And could you tell us how many water does the plant consume? Well, the quality of the water is it's really good. It's a really high quality. We are talking about ultra pure water with less than 5 microsiemen of conductivity. And this stream of water can be directly used in a chemical process that requires this kind of purified water. In the pilot plant, we don't produce so much water. Most of the water is used for the humidifier, but we have an excess of water. So we could take advantage of this in an industrial site, and this stream could be used for another application.
Yeah.
And Sonia Ferreres from Spain also. If we can talk about the pretreatment or purification step in the hydrogen stream coming through the plant. Well, actually, the hydrogen that we use has a really high quality, and we clean it with the same equipment which humidify the hydrogen is used for remove the pollutant. So we use a water shower that goes
countercurrent. Yes.
Countercurrent to the inlet hydrogen and remove all the pollutant that can be with the gas flow, and in order to avoid any damage of the fuel cell. It's a really simple treatment.
Yeah, but it depends. It really depends on the composition of the hydrogen stream. So
yeah, this is our case. In
our
your pilot plant. I mean, but it depends on the final destination, of course.
Yeah, it could be a simple scrubber, like Maria says, or it could be something more complex. Next question is Dimitri from Belgium. Would it be possible, interesting to use this as a CHP power plant where the heat produced by the fuel cells will be recovered and stored for external usage? And what could be the efficiency of such process? That's a very good question, because we didn't have much time to go through the applications, but the system has a 50% electric efficiency. The system has a heat ratio of electricity and heat of 1, so it produces a good. If you have 1 megawatt of electric power, you also have 1 megawatt of heat capacity. So yes, definitely is great. It has great potential to be used as a cogeneration, especially in district heating, because we are using low temperature PEM fuel cells. The temperature of the water stream is around between 75 and 70 degrees. So we're not talking about high temperature heat, but it could be really good for district heating or even the preheating of other streams. So yeah, absolutely. And this is a really good added value if we add also the water, because when you are making a potential economic case of a hydrogen plant, you are not only talking about electricity, you are also talking about heat, and you're also talking about very good quality, like Maria said before, purified water that could be injected directly even in chemical process, even in the feed, the makeup water of conventional power, steam power plants. So yeah, there is a lot there.
And I think the last one.
Yeah, and the last one from Alejandro Munoz, which is the minimum time slot for power selling in the energy market in the Netherlands. 15 minutes, 30 minutes. So
maybe George, you could answer.
Or maybe Marianne from Romania. So what I can say is that we are using 15-minute slots to quantify the energy. So we are using 15 minutes.
But maybe Marianne.
But yeah, maybe Marianne has something.
A better answer.
Well, yeah, typically is the 15 minutes if we are talking about the energy trading. The other things are the reserves, where the response should be much faster. But for the energy, 15 minutes is okay. But I'm not sure about. I'm not completely sure about the Netherlands itself. So that's something that we should still take because it's changing all the time.
Okay, so I think that we don't have more questions. Anyway, if you have any doubt or question not solved here, you can contact us in the email that appears in this slide. And also, if you are interested in building a megawatt scale plant, power plant. So thank you very much for your assistance. We hope you like it and enjoy it with the webinar and the presentation. And thank you also for all partners for your contribution. Remember that you will receive the recorded of this webinar and the presentation in a few days. And don't hesitate to contact us for any question or queries. So I think that's all. Have a great day. Bye-bye. See you.
Yeah, thank you.
Thank you. Thank you, everyone.